Here we're finding the decomposition of a rational expression when a denominator has a repeated irreducible quadratic factor. Now, the partial fraction decomposition of a rational expression when the denominator has a repeated irreducible quadratic factor and the degree of the numerator is less than the degree of the denominator. So we're going to write the denominators in increasing powers. So given a rational expression that has a repeated irreducible factor, we're going to decompose it. Number one, we're going to use variables like a, b, or c for the constant numerators over linear factors and linear expressions such as a1x plus b1, a2x plus b2, etc. for the numerators of each quadratic factor in the denominator written in increasing powers. Then we're going to multiply both sides of the equation by the common denominator to eliminate fractions. Number three, we're going to expand the right side of the equation and collect like terms. Number four, we're going to set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. So, in example number 4, we're going to decompose the given expression that has a repeated irreducible factor in the denominator. And the repeated irreducible factor in the denominator is x squared plus 1 squared, which means we can't factor that any further, and it's being repeated because it's squared. So the factors of the denominator are x squared plus 1, and x squared plus 1 squared. And recall that when a factor in the denominator is a quadratic that includes at least two terms, the numerator must be of the linear form ax plus b. So let's begin the decomposition. So here we have our rational expression on the left side. We have a divided by x plus bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 squared. Number 2, we're going to eliminate the denominators by multiplying each term by the LCD. The LCD is x times x squared plus 1 squared. So we multiply the left side and we're left with the numerator. Multiplying it by the right side, if we eliminate the x for the first term, it's going to be a times x squared plus 1 squared. If we eliminate the second term, we're eliminating one of the denominators, which would be x squared plus 1. So we're going to end up having bx plus c times x squared plus 1. Plus, if we eliminate the denominator, which is x squared plus 1 squared, then we're left with d plus e times x. So now what we're going to do is we're going to expand the right side. By expanding the right side, we're leaving the left side alone, and over here we're going to expand this expression. X squared plus 1 squared is x to the 4th plus 2x squared plus 1. And then we're going to expand this one. So we're going to take bx plus c and multiply that by x squared plus 1 and leave the x on the outside for now. When we FOIL that, we get bx cubed plus bx plus cx squared plus c. Then over here we're going to leave this alone, so we're just going to make sure that we can leave this as x times dx plus e. And now by expanding, now we can distribute the a. So we get ax to the 4th plus 2ax squared plus a. We're going to distribute the x. So we get plus bx to the 4th plus bx squared plus cx cubed plus cx. And then we're going to distribute the x here to get dx squared plus ex. And now what we're going to do is we're going to collect the like terms. So by collecting the like terms, we can see that we'll end up with 5 equations. And those 5 equations are the following. We have factor out the x to the 4th, so we have a plus b, which is equal to the coefficient of x to the 4th, which is 1, so we have a plus b equals 1. We have the x cubed term, and that has a coefficient of c, and it's going to equal the coefficient of 1 here for x cubed. So we have c is equal to 1. For the x squared term, we have 2a plus b plus d, and that's going to equal the coefficient of x squared on the left side, which is 1. And then the x term, we have c plus e. It's going to equal the coefficient of x, which is -1, so that creates equation number 4. Equation number 5, we have the constant, which is a, and it's going to equal the constant on the left side, which is 1. So what we've noticed here is that we've already been able to at least solve for equation 2 and 5. So c is equal to 1 and a is equal to 1. So in step number 6, we can use substitution from this point. So we're going to substitute a is equal to 1 into the first equation to solve for b. Plugging in 1 in for a and subtracting 1 to both sides, now we know that b is equal to 0. And in step number 7, we can substitute a is equal to 1 and b is equal to 0 into the third equation. So we have 2 times 1 plus 0 plus d is equal to 1. If we subtract 2 to both sides, now we know that d is equal to negative 1. And then we're going to substitute c, which is equal to 1, into the fourth equation, which is c plus e is equal to negative 1. Substituting c to be 1 and then subtracting 1 to both sides, we now know that e is going to equal negative 2. And now that we have solved for all of the unknowns on the right side of the equal sign, we have a is equal to 1, b is equal to 0, c is equal to 1, and d is equal to negative 1, and e is equal to negative 2, then we can write the decomposition as follows. So if we come back up here, we can see here we're going to substitute all the values that we have for those ones that we had solved for. So we end up getting 1 over x plus 1 over x squared plus 1 minus x plus 2 divided by x squared plus 1 squared.